Okay, let's talk about heat engines. Heat engines, of course, are a system where we can convert thermal energy into work. And we've talked about the fact that the work done by a heat engine over an entire cycle, if we graph this path, again, we say we start from some initial point, we go around, round, and round, and then we return to this during each cycle. It is the area contained within this path or encircled by this path, which is going to be related to the work for each cycle. Now, it's important to notice that we're returning to the original state. Wherever we're starting, that's where we're going to stop. And therefore, in a cyclical process, the internal energy that we end up with is going to be equal to the internal energy that we started out with. Okay? The heat that we have to put into the system will be equal to the work that we take out of the system. Okay? So the net work done by each cycle is equal to this area contained within this path. And that's represented by that integral right there. Normally we just use a regular integral sign to denote we're looking for the area underneath the curve. When we have a closed path, the area contained within the path is represented by that integral with that little circle on it. Okay, so what are we doing with a heat engine? We are taking energy from some high temperature source, what we call the hot reservoir. We allow that to be transferred into our engine. So heat comes in, QH, that goes into the engine, that does work, and then it is dumped into a cold reservoir, usually dumped into the environment as QC. Now, if we take a look at this expression right here, conservation of energy says that QH is going to be equal to the heat that we exhaust, QC, plus the work that's done. So basically, the work that we get out of the system is going to be the difference between the heat that we get from the hot reservoir minus the heat that we dump into the cold reservoir. And the more efficient our system, the more work we can get done for a certain amount of QH. Okay, again, conservation of energy. The energy can either become work or the energy can become exhaust heat. Okay, so in general, the heat engine will produce some work, but not 100% of the input energy is going to be turned into mechanical energy. And again, just taking a look at conservation of energy, if QH is equal to QC plus W, the work that the engine does every cycle is equal to the amount of heat absorbed from the hot reservoir each cycle minus the amount of heat that is expelled generally into the environment, the cold reservoir in this. So for instance, if we were looking at an internal combustion engine, we would say, well, the hot reservoir would be the combustion of the fuel and the air, right? That's where the energy is coming from. Chemical energy is being converted into heat, okay? This heat is then used to drive a piston. This does work. And then what happens to the hot gas, which has been used to do work? Well, it's expelled into the environment out the exhaust pipe, okay? This could also be a power plant. We could imagine that there's some source of energy, again, that's heating up the boiler. The boiler then generates steam. The steam goes into the turbines. The turbines turn to create work, and then that heat is exhausted out into the environment. So heat engine basically works the same way for a number of different systems. We have a source of energy. Typically, we call this the hot reservoir, even though theoretically, the source of energy might not necessarily be hot initially. Like the fuel-air mixture is not hot initially. It contains chemical energy, which is turned into heat. Some work is done, excess heat is exhausted into the environment. Even humans, to some extent, are heat engines. We can think about us with glucose being one of the primary sources of energy plus oxygen. Although this is not turned into heat directly, okay, that energy is transferred into the muscles. The muscles will do work, and while doing so, they'll generate heat, and this heat will be dumped into the outside environment. That's why we are homeotherms. We maintain a constant temperature, and we're constantly giving off heat, which makes it into the outside environment. So again, let's take a look at a typical heat engine and see how we're going to do this. All right. We know when gas expands, work is being done on the environment. When gas is compressed, the environment is doing work on the gas. So if we look at our PV diagram, our pressure versus volume diagram, okay, we know the work that's going to be done is equal to the area that's underneath this graph. Okay, so we want this line to be as high as possible. We want that function to be at the greatest pressure possible when we go from left to right, because that'll maximize my area underneath here. So the whole idea of a heat engine is allow the gas to expand while it's hot. Okay, put the heat in, however you're going to do it. Maybe it's chemical energy, maybe it's nuclear energy. Some source of energy is going to be converted into heat. That heat is going to heat the gas. Gas is then going to expand, put a force on the outside world, do work, and that work will then be utilized. Okay, so at least during the expansion cycle, we want hot gas at a high pressure. But to repeat the cycle, to get back to the original state, we need to, after the gas is expanded, compress the gas back to its original level. Now, we want to expend the least amount of work returning it back to its original state. So what does that mean? That means make the gas as cold as possible by removing as much heat as possible. Okay? Again, the PV diagram. Draw that once again. When we allowed the gas to expand, we were up here. We're going from left to right, and we could utilize all this area underneath. Okay? Now, we're going to do just the opposite. We're going to go from right to left, but we're going to do it at a very low pressure. Low pressure means low temperature by the ideal gas law. So the negative area that I lose, okay, is going to be much less than the positive area that I gain as I do the work. Okay, so in the previous case, I was getting work out. When I compress the gas, I'm having to put work in, but let's say, for example, I get 1,000 joules out when I allow the gas to expand. Well, I only have to return, let's say 300 joules when it's compressed. Okay, that's a pretty good trade right there. That means that overall, I'm getting 700 joules every cycle. Okay, only had to put 1,000 in, I'm getting 700 out. 70% efficiency is actually excellent for a heat engine. Okay, so again, heat engine, we allow expansion at a high temperature, we recompress the gas at a low temperature. And again, if you can look at this right here, this is a little bit tough to see on this path. From this point to this point, this corresponds to expansion. Okay, we're increasing our volume, from point A to point B. And then the other way around, that would be compression. Okay, so if we look at the area, here's point A, here's point B. During the expansion phase, I got this much area, right? Okay. During the compression phase, I gave up this much area. So the total work done during this entire process was all this in here. Okay? Everything the yellow. That's all the work that's being done. All right? So again, that takes into account the work that we gain during expansion and the work that we lose during compression. Let's do an example of a heat engine, and this will illustrate it pretty well. What I have here is I have a 3-part cycle. I have isochloric, increase in temperature from A to B. I have isothermal expansion from B to C. And then I have isobaric compression from C to A. It's going to return to my original state right here. Okay, let's calculate for each of these different phases. The gas begins, oh, by the way, number of moles, 0.203 moles. The gas begins with a volume of 5 liters and a temperature of 300 degrees Kelvin, pressure of 1 atmosphere, okay? And that's 10 to the 5th pascals, by the way. The gas is heated to 900 degrees Kelvin, so we go from 300 to 900. While the volume remains fixed, it's isochloric, no change in volume, so no work. The gas is now allowed to expand isothermally from 5, okay, to 15 liters. Calculate the total work done by the gas in one cycle. Okay, let's do that. So again, A to B isochloric, there's no work being done. B to C isothermal, and then C to A isobaric compression. So once again, I'm just heating the gas from A to B. Q is coming in. Yes, that's true. So we are changing the internal energy, but no work is being done. Okay? Just brings me from A to B. After I do that, now I'm going to go through the isothermal expansion. Okay? And during the isothermal expansion, we're still adding heat. Okay? But this time, notice the purple line, we have area underneath it. We have all this area underneath it. And that's going to be the work calculated using this equation right here. Okay? Now, let's plug in our numbers. We have 0.203 moles. There's R, that's always 8.31. We're expanding isothermally at 900 degrees Kelvin, and we go from 15 to 5 liters. By the way, notice I don't have to change this to meters cubed, okay? The liters divided by liters cancels out, so it just becomes the natural log of 3. There are no units in there. I didn't have to do any conversion. So I calculate that, and I get, okay, when I allowed the gas to expand while it was hot, I got 1670 joules of work out of this, okay? So 1670, that's how much positive work the gas is going to do as it expands. But now I need to recompress the gas to get back to A. I'm right here in the diagram. Let's see. I need to get back to A. So I'm going to undergo an isobaric compression. When that takes place, I am removing heat from the system because I'm going from 900 degrees Kelvin to 300 degrees Kelvin, all the while compressing that gas. Okay? Now, for this case, I again can calculate the area. Okay? And again, this is going to be negative area technically because we're going from right to left. So work equals P delta V. That's this equation right here. My pressure is at 1 atmosphere, 10 to the 5 pascals. I'm going from 15 times 10 to the minus 3 meters cubed. Remember, 1 liter is 10 to the minus 3 meters cubed to 5. So that's negative 10 times 10 to the minus 3. And the work from C to A, should be a negative sign here, is going to be 10 to the minus 2 times 10 to the 5. That gives me 10 to the 3, or 1,000 joules. So negative 1,000 joules doing that. Okay? So again, let's review. When the gas expanded, I got 1670 out of it. When I had to recompress the gas, I lost 1,000. So looking at my net work being done, 0 from A to B, 1670 from B to C, negative 1,000 from C to A. That's one complete cycle. That's the area right here, is going to be a net of 1670. I'm sorry, 670. 1670 minus 1,000, 670. Okay? So that's how we calculate the work done by one complete engine cycle. There were actually 3 phases to this: isochoric, isothermal, and isobaric. And if I add the work during each phase, I get the total work done by a complete cycle. Okay. Now, there are different types of heat engines, and really, of course, the most important heat engine that started everything was the steam engine. And of course, the steam engine, we took energy from a boiler. Okay, that boiler would be heated by some fuel, normally coal. This steam would go into a piston, which would be the heat engine. The piston would expand, do work, and then the excess heat from the steam would be dumped into the environment. Steam would be cooled or would be exhausted. And that's how the steam engine would work. Now, the first steam engines were very, very inefficient. Thomas Newcomen, who was a blacksmith, invented the first steam engine to pump out water from a coal mine. Kind of funny that these steam engines were powered by coal. In order to mine the coal, you had to remove the water from the mines, and that would require the burning of the coal. So these Newcomen steam engines were revolutionary, but again, very inefficient. They wouldn't move very much water for the amount of energy that you had to put into them. So of course, somebody came along and improved on this. And this was James Watt in 1763. He was able to separate the steam condensation system. And in doing so, he greatly improved the efficiency of the engine. What he essentially was doing was making it so much easier to recompress the steam by cooling it or condensing it back into water. Okay, so James Watt, of course, we rewarded his improvement of the steam engine by naming the unit of power after him. Now, the steam engine is, obviously works on steam, was a very dangerous thing to operate originally. The steam engine itself was actually more advanced than the metallurgy of the time. And the weak metal that the boilers were made out of meant that any pressure spikes could cause a steam explosion. Many of the steam explosions were due to the fact that they would heat the water in these heat exchanger pipes. And as the water in the boiler would slosh back and forth, a pipe could be basically left exposed with no water in it. It would rapidly heat, and when the water would slosh back to the position that was being heated, it would flash boil, and this would create a pressure spike which could destroy the whole boiler. So here's an actual photograph of a steam locomotive that blew up during one of these incidences. And you can see it's pretty much ripped inside out. But not only would you have explosions from these locomotives, which would be just dangerous to the operator, you could have the steamship explode due to these flash boiling. So again, as time went by, they were actually able to improve these boilers, so you didn't have the flash heating. But again, the metal used back then was still relatively weak compared to the metal that we use today. Now, steam engines are using steam. Steam is not an ideal gas. So when we look at the cycle which is used, it's called the Rankine cycle. It basically works by boiling the water, okay? It causes the pressure to jump, allowing the steam to expand adiabatically, and then recondensing the steam at a constant pressure, okay? Now, the problem here is when we draw our P versus V diagram, there's actually a phase transition that happens in the middle of this. And this is where water is a liquid over here, water is a gas or steam over here, but it's both a liquid and steam in the center part right here, okay? And again, this is known as the Rankine process, okay, or cycle. And of course, in the first steam engines, they used a piston. We now know today that it's actually more efficient to use a turbine in the case of power plants. The turbine can allow for the steam to expand continuously, whereas the piston has to move back and forth. So the turbine, with its continuous motion rather than its reciprocating motion, is just a much more efficient system. But again, you can see that the boiler converts the water into steam. The steam then expands through the turbine. It is then condensed from some outside source and then is recirculated to the boiler, okay? So again, it could be a fossil fuel, which is generating the heat. It can be a nuclear power plant or nuclear fuel or nuclear reaction is generating heat. But in either case, the process is pretty much the same. The power plant generates steam. The steam's energy drives the turbine drives the generator, and the generator turns the work into electricity. And again, here is a schematic of what it looks like. We have some heat input, which goes into the boiler or heat exchanger. The steam then drives the turbine. It's then recondensed, where energy is dumped into the environment, and then it's pumped back into the boiler again, or steam generator, whatever it is. Again, this is what the cycle looks like. Heating the water up to its boiling point, And then as it's allowed to expand, it goes from a liquid to steam. And then basically, this powers the turbine. So the Rankine cycle. Internal combustion engines, yes, are a little bit different from the external combustion engine, which is a steam engine. In the steam engine, you have external combustion that generates heat. The heat goes into a boiler, and then the steam is allowed to expand, driving a piston or driving a turbine. With the internal combustion engine, the products of the combustion actually drive the piston. So, in some ways, it's sort of a convenient system in that the natural gases which are generated during combustion are actually the ones doing the work. And this is what it looks like. We start out with a fuel-air mixture, which is brought into the cylinder. The piston goes down, then it starts heading back up, and it's going to compress this mixture right here. A spark, if it's a gasoline engine, or just the auto ignition, if it's a diesel engine, will cause the gas to get very hot. The gas expands, pushes down on the cylinder, and then after it's done its work, it's sent out this exhaust tube. Okay, so you can see we have the gas, which is compressed, gas fuel mixture, which is compressed when it's cold. It's allowed to expand when it's hot. Okay, and then the excess heat is dumped into the environment as exhaust. And here is a 4-cycle engine, and you can see how it's going through here. Okay, the blue represents the fuel-air mixture before combustion's taking place. Combustion is shown as orange, yellow, and red, and then the black shows the spent exhaust, which is sent out of the system. And you can see that not on every trip do we get a power stroke. Only when you see that orange do we see a power stroke. Okay, so every other cylinder, every other part of the cycle. And again, this is what it looks like from the green line on the bottom right here. We go from the air fuel mixture being compressed from here to here. Okay. After it's compressed, it ignites. Okay. Fuel air mixture is adiabatically compressed. Work is done on the gas. Spark plug ignites the fuel. Okay. So again, sorry, I sort of, it's a little bit confusing right here. Right here, it's going to be compressed. Ignition goes from here to here. It does the power stroke from here to here. Then from here, back and forth, it's getting rid of the exhaust. So the hot gas is expelled, it's exhaust removing the heat from the cylinder, and then the whole process begins again. Now, gasoline engines have become more and more efficient, but it's come at a cost. The poor efficiency of the gas engines were generally due initially to the low combustion temperatures, other factors, but now we've not only made the engines much lighter, we've also made the internal pressures and temperatures much higher. Unfortunately, this means that the engines wear out much faster. These are the rings which are used to seal the pistons inside the cylinders. And obviously, the hotter the temperatures become, the weaker the material becomes, and the more easily it's worn down. So higher internal pressures, higher temperatures have benefited us in terms of efficiency. However, they also increase the general wear and tear that the engine experiences. They have been, coating some of the components with ceramics, and this makes them able to endure much higher temperatures and pressures, and also reduce the amount of heat transfer to the interior of these components. Diesel engines are much more efficient than gasoline engines generally due to their higher compression ratios. The problem is when diesel engines aren't operating ideally, they have a lot of incomplete combustion, which leads to soot. So newer engines are designed to operate more ideally. Again, here's the diesel cycle. It's a little bit different from the gasoline cycle or the Otto cycle. Okay. But as you can see, oh, and a diesel engine doesn't have a spark plug, because what happens here is as we compress adiabatically, the diesel air mixture, it reaches a point 2 where it auto ignites. So from 2 to 3, suddenly there's a huge increase in the amount of energy of the system. It's allowed to expand, and then it expands adiabatically after the ignition, and then exhausts out the excess energy down here. Turbine engines are also heat engines. However, instead of a piston, we use a continuously rotating turbine. And instead of the gas undergoing different pressures and volumes at different times, it's happening continuously where the gas is experiencing different things at different parts of the engine. Now, this is a jet engine. It's a gas turbine engine. This is also similar to what would happen, well, at least partially, in the turbine of a power plant, although in a power plant, you don't have internal combustion like you do here. But again, in a turbine, you're allowing the gas to expand, and as it expands, it does work on the turbine blades, and this work is used to power a system. Now, for this jet engine, we take air in, okay? It is compressed with these compressor blades to higher pressure, then combined with fuel, it ignites, drives these turbines on the back end, which cause the entire engine to spin, and that powers the compressors up front. So fresh air comes in, hot, high pressure gas leaves, doing work on the system. Okay. Now, if we were to diagram this, the Brayton heat cycle engine, which is effectively the engine cycle that they use on these, looks like this. Okay. You have adiabatic compression of the air coming in. You then have the ignition of the air. Okay. And then you have the air expanding at the back end. Oh, it didn't change color. Okay, so it's expanding on the back end. All right. And then finally it's removed and the whole cycle begins again. So none of the same gas is going to participate in the cycle. Once it's gone through, it's gone. But again, this is not a cycle where we start at one point, we end up at another point. This is a continuous cycle. The air is constantly coming through this engine. And again, for all these different cases, the heat engine, we have energy which is coming in form of QH. All right. Some of that is converted into work. Some of that is just converted into heat that's going to be exhausted out. Now, if we look at the efficiency of a heat engine, we want to see how much work we're able to do, okay, compared to what is the total input. Now, once again, if we go back to the other diagram, we look at QH, sorry about that, we look at QH as being the energy input, okay? QH is the energy input, all right? W is the useful energy. And whenever we look at efficiency, it's always useful energy divided by the energy input. So coming up with an efficiency here, efficiency is defined by work divided by QH. Since work is QH minus what we lose in QC, we can also write it this way. And if we take the first term and divide it by QH, we get 1. The second term divided by QH, we get QC over QH. And that becomes our expression for efficiency. Either the work divided by QH or 1 minus QC divided by QH. The more work we get, the higher the efficiency. The more energy we exhaust into the environment, lower the efficiency.